Good morning or good afternoon, depending on where you are at. My name is Atarut Azizin Amini with Florida International University. Before we start, we wanted to share with you some good news. The 2022 conference will be fully in person. So no hybrid, no virtual. It's going to be fully in person, and it's going to be in Miami, Florida, and of course, no place better than being in Miami, Florida in December. So December 2022, between 7 and 9. The conference will be actually on December 8 and 9, Thursday and Friday. But then day before the conference, we're going to have a series of a workshop, and the workshops are going to be finalized very soon. So 1 day workshop and then 2 day the conference. The call for abstract. The deadline was February 25, but we have extended because of the some folks would like to have a little more time for submitting the abstract. So the new deadline for submitting your abstract is April 12. So April 12, 2022 is the deadline to submit your abstract. And the conference also includes opportunities to exhibit at the conference. So if you are would like to share the services or products that you have with our audiences, please consider to exhibit. We usually get close to 60 exhibits. Many state DOT engineers attend the conference. In fact, in each one of the conferences that we've had more than 100, 150 state employees that attend these conferences. So it's a very nice place to showcase your product. So to submit your abstract, please go online, go to our website, go to the conference page, and you can submit your one-page abstract online. Again, the deadline is April 12th.
Our presentation today features the world's longest Pultruded pedestrian bridge, the Flats Inlet fiber-reinforced polymer pedestrian bridge on the island of Bermuda. We'd like to thank Professor Armin Mehrabi, co-director and director of research at the ABC UTC, for coordinating this presentation. We're pleased to welcome our presenters, Tucker Murphy, president of the Friends of Bermuda Railway Trail, and Dan Winey, chief structural engineer of the ET Techtonics product line with Creative Pultrusions, Inc. Tucker?
Thank you very much, Mary Lou, and good afternoon, everyone. Thank you for joining us today. I'm Tucker Murphy. I'm president of Friends of Bermuda Railway Trail, and I'm actually a biologist by training. So if you have any engineering questions, please direct them to Dan. But I'm going to give you an overview of the project, why we did it, why it's important, and some of the challenges we faced, and then turn it over to Dan for some of the design and technical information. So without further ado, let's get started. So I'm also Bermudian. This is a picture of my country. For those of you, I'm sure some of you are familiar with it. Some of you may not be, but we're a tiny little island in the middle of the Sargasso Sea in the Atlantic Ocean. We're about 21 square miles total, and we're actually the second most isolated island in the world, far away from the mainland and any other islands. We're also incredibly densely populated. We have about 60,000 people on our small island. And as a result, it's a very urban place. We're classified as actually almost 100% urban. So everyone's living. We're living right on top of each other. As a result, because we're so constrained by space, national parks are very important here, and actually our our biggest national park and our longest linear park is an old railway trail. We had a train that ran here for about 17 years, and the trail has been preserved into modern day. So back in 2012, I had come back to Bermuda from my university, and I decided to set up a charity called the Friends of Bermuda Railway Trail to attempt to enhance and reconnect this national park and turn it into a continuous route for pedestrians and cyclists. But this project is associated with many challenges. In particular, we're one of the saltiest marine environments in the world. We're also hurricane prone, and the original rail line had 33 bridges and trestles. So we knew that anything we did to reconnect it would have to meet our tough and environmental circumstances and be able to withstand hurricane force winds. And if you look at the two places we started, you can see on the map. The first place we set out to reconnect was Bailey's Bay, shown by the blue arrow, and then the second spot was Flats Inlet, shown in red. Flats is what we're going to focus on today, but I'll just give you a brief overview of Bailey's Bay, because that's where it all began. That's where we became familiar with FRP bridges. So here's a picture of Bailey's Bay. These are the bridges that were completed in 2014. Basically, this project actually went very quickly for us. We raised the funds and we set out in 2013 to build it. We contacted a group called Techtonics, which is now under the umbrella of Creative Pultrusions, who Dan is affiliated with. And we talked to, at the time, there was a fellow called Eric Johansson, who was the founder of Techtonics and the lead engineer. And he introduced us to these fiberglass bridges, which had many advantages for us for this project. The pylons were pre-existing, and the bridges could be shipped in containers and assembled off-site in a location called dockyard, and then barged into place. They were assembled by volunteers, and myself included, and Parks Department employees. So with the success, well, we constructed these bridges, and we found that we had great success in terms of trail use. The average trail use per week increased about tenfold, and it exposed locals and tourists alike to one of our greatest assets, which, aside from the friendly people, I'd say is the turquoise sea. That's really one of the highlights of our environment here. So with that, we decided to take on a more ambitious project, Flats Inlet. To give you an idea, Bailey's Bay was about seven bridges. Flats Inlet, the total stretch is longer and higher, particularly the central span. It's about 150 feet. And this is a picture of the historic railway bridge at Flats. You can see this was actually even higher than our new pedestrian bridge. It was about 40 feet in the air, so high that I heard even at one point a plane flew underneath it. But it didn't last very long. Our railway age came late and was kind of short-lived. It was finished in 1931 and only lasted until 1948. And part of the issue was that our harsh natural environment led to many maintenance problems. The towers which the trestles are built upon were made out of wood. They rotted quite quickly. I've been told that the ends weren't soaked in creosote, so that was a big problem. And then also the tracks and the truss on top were constructed out of metal. They corroded and deteriorated very, very quickly until a point was reached where it wasn't worth the it wasn't worth the cost to try and continue the railway trail, or sorry, the railway train, and it was reverted back to a national park. So this is what the site looked like when we began the project. As you can see, it's very different from the railway age, and this is really where the longest fiberglass bridge began. It wasn't something we were seeking to do originally, but it was something we needed for our site conditions. So Dan's going to tell you a little bit more about that. Over to you, Dan.
All right, thanks, Tucker, and that's a great introduction to this project. So we were tapped to do this. Sorry, I'll go back a slide. Creative Composites group, which Creative Pultrusions is part of, and we have the ET Techtonics product line, in which Eric Johansson, we call him Rick. Even in this project, Rick Johansson had oversight of the design with me of Creative Composites group. So just want to say hello to all of you. Thank you for being to this presentation. Both Rick and Creative Pultrusions, Creative Composites group, we have a long standing relationship with our fabricator, who is next to our manufacturing plant or nearby, Structural Fiberglass Incorporated. So we have had this long-standing relationship, and as you see, we even had that relationship during the Bailey's project, so Bailey's Bay project. There was one major hurdle, so I'm going to take you back into history a little bit before we discuss that. It's the end of this slide. We'll talk about that a little bit. So as Tucker related to, he has a great relationship with Rick Johansson. In the 90s, he received a research grant from the National Science Foundation, and he began designing U-type structures. As you saw in Bailey's Bay, that's a U-type cross-section, fiberglass bridges. They were pre-assembled. They could be delivered either pre-assembled, partially assembled. In other words, we will assemble the trusses only, and then the contractor or volunteer association will put them together, or we can just send them in component parts, and we send assembly drawings. That's how Tucker and them got their bridge in component parts, and they assembled it in Bermuda. Additionally, there were additives put in the resins for ultraviolet protection. And on this bridge, the top members of the bridge are painted also by a polyurethane paint. So all these bridges are assembled from FRP, fiber reinforced polymer, Pultruded profiles. Pultrusion is a process that takes resin and reinforcements, e-glass or glass, fiberglass glass as reinforcement, and it heats it up together, and in about 6 to 8 feet you can have a shape, structural shape. For this bridge that we're going to get into, the channels were used, shape was used for the top and bottom chords, the stringers, railing, and cross pieces. You'll see pictures of them soon. Tubes, both filled or fully solid or partially solid, are used for the post diagonals, X bracing, and horizontal bracing. Design history, Rick instituted a Howe truss bridge, and he mostly used 2 of them for the U-type structure, either with diagonals or X bracing. When X bracing was utilized, which you'll see on this bridge too, there are both compression and tension diagonals. The standard bridge is a U-type typical cross section. These bridges have minimal structure depth, and for construction, that is great for hydraulic to keep that structure depth low and to keep the structure above or as high as you can above the floodplain. And also the low structure depth provides minimal approach work. As far as the approaches, they don't have to be as high because that structure depth is low. Previously, the longest FRP truss bridge length was around 120 feet. And as Tucker alluded to, the main span at the Flats Inlet project site was around 150 feet. So there, or herein, lies the hurdle that we had to break or cross over. Our standard widths are 4 feet to 10 feet. And Flats Inlet Bridge, it's the first boxed type typical cross section. Rick and Tucker can acknowledge this. Tucker and them wanted to look, the aesthetic of the bridge to look like the railroad trestle. So we utilized a box type structure. As far as design and testing of the main span bridge, we designed this according to the Bermuda Building Code, which references the 2015 International Building Code, and ASC 710, which is minimum loads for structures. And of course, this structure would be an other type of structure. We utilize allowable stress design method. This method is utilized mainly because AASHTO and the building code have not come out with LRFD fee factors or parameters for Pultruded members. We are expecting the building code to produce these or publish these fee factors for LRFD design very soon. So this project, a concern, and Bailey's Bridge, all those bridges that you saw the previous project, they have withstand type 4 and type 5 hurricane winds. So the hurricane wind on this load was considered to be 158 miles per hour. That's our velocity, which results, as you know, the building code modifies that load by a factor for service load of 0.6. So the net design pressure on this structure is 67 pounds per square foot applied to the side of the structure as if enclosed. So it is fully enclosed, not just the structure itself. So, and we do that for our bridges because that is in the 2018 AASHTO guide specifications for the design of FRP pedestrian bridges. And normally they suggest 35 pounds per square foot as if in an enclosed structure, and that is based on 100 miles per hour. So as you can see, if you're a AASHTO designer, this was a little different. But I just added some of this stuff for your comparison. For AASHTO LRFD 2002, and this is in the reference section, your last slide, all these are referenced. For service load design at 158 mile per hour wind, the net design pressure would be 87 pounds divided by an overstress factor, which would equal about 70 pounds per square foot as if an enclosed structure. So very close or similar numbers, whether you're using the building code or AASHTO. The live load for this structure is reduced to 65 pounds per square foot as permitted by the International Building Code. And you AASHTO designers, if you're familiar with the pedestrian code, that would be 90 pounds per square foot. The dead load of the structure, which is very important in FRP, as you know, it's a lightweight material. many times, probably 4 or more times lighter weight than steel. So our total dead load was around 60,000 pounds. So that's light. And we'll talk about the advantages of that for Tucker and construction later. The design process of this main span. First, Rick and I modeled the design, finite element analysis of the box truss structure. And so we came up with some general loading. Then we went to the universities of Miami and the University of West Virginia and had our members tested. The photo on the side is a testing of a 3-foot long tube member, and we're testing its compression capabilities. From that, we developed the Euler buckling graph of our compression members, and also we would have testing these members in tension, as well as those channels as mentioned before. And then finally, for connection design, many of you are interested in the connection design of these structures. Well, essentially, we don't calculate connection design like you do a steel bridge. We take our material and we set up an apparatus and we test it and validate those connections through bearing tests. And so we do our connection design based on actual tests. And that's all we really have. We don't have a standard like the steel manual. So this is how we come and validate our members. The final design then was completed. Once that testing was completed, we could go back to our design and make sure our components and connections were safe and okay. Another facet of the design or in the design process was to see what kind of crane Tucker and them have on the island and check that for our load. So that was part of our design process. The next step was we pre-assembled our bridge at our factory for testing. That testing then, when we have it assembled, it took about 2 weeks to disassemble it. Again, this is the first time we ever did a box type structure. And our members were larger than normal. So we assembled it in about 2 weeks. The testing, we tested the full structure to 110% of the uniform live load. And we'll show you eventually how we did that. So we tested it to 72 pounds per square foot of uniform load. And also during our testing, we had a local crane company pick that structure up 20 feet in the air, just as it would be picked in Bermuda. So here is just some general design dimensions, and you can see the structure here in our yard that is assembled, except for some of the railings not there. Generally speaking, center line of center of truss dimension was 8 foot 3 inches. Again, it was a box structure type section. There were 20 bays at approximately 7 foot, 7 3/4 inch spacing. As you can see in the yard, the bottom cord length, right here, the bottom cord length was 152 foot 2 inches. The center line of bearings, and we're going to show you a picture of that, what the bearings look like here shortly. They were 148 foot 8 inches, center to center bearing bridge length. Some of the facets of design before we get into the construction of it and assembly. Containers are limited to 40 feet when we are going to ship this bridge. So our maximum member, as you can see here, is 38 foot 1/4 inch or 3/4 inch. I have that in the wrong number in the slide there on the text, but that is part of the plans there. 152 foot 2 inch bottom cord shown. We used a 28 3/4 inch diameter A316 stainless steel bolt splice. All bolts or hardware were A316 designation. The weight of that longest member in the middle, 38 feet, is approximately 226 pounds. So 2 people can take that member and move it into place. The compression members were checked at splice locations with top chord splices controlling the design. We located those splices as far as possible away within those limits of shipping containers. Just for a quantitative number, the design force at the splice length was 94,000 pounds at about 0.375 times the span length. The allowable value was around 135,000 pounds at this splice location. Another facet of design, because FRP is lightweight, we must check frequencies. AASHTO, the 2018 AASHTO guide specifications for design of the FRP pedestrian bridges requires vertical frequency of 5 hertz and transverse frequency of 3 hertz minimum for negligible risk of vibrational issues. Essentially, the vibrational issues can cause troubles. When you have synchronized pedestrian use of a bridge, that synchronized dynamic force can cause vibration, and which results in deflection of the structure. And if that is continued, it will accelerate and essentially make the bridge fail. Actual frequencies, and we mostly model our bridges without decking, knowing that that decking will help with diaphragm action, especially in the lateral or transverse direction. They were 2.88 hertz in the vertical direction and 2.587 hertz in the transverse direction of the bridge. That may look a little alarming, so let me explain with the next slide. As referenced in the AASHTO, current AASHTO pedestrian design specifications, there is a document that's referenced from Europe. In fact, it's part of the France Association of Civil Engineering. It's called the 2006 CITRA document, and that's referenced in the last slide also. The full reference is. We looked at this after we designed the bridge, and we went through an analysis as required by that method. Essentially, it looks at acceleration of the bridge during synchronized pedestrian motion. Now, if you remember, those numbers that I gave you before were based on natural frequency in hertz. So this is a better indicator of what kind of comfort you're going to have. So we went through this, and I'm going to show you this graph a little bit. We looked at it in both directions. So this is part of that CITRA document. Again, if it meets the AASHTO requirements, then we are negligible risk. As you can see here in the direction of each direction of the bridge, looking at the acceleration, we ended up with a low risk of vibrational troubles. And then it's categorized as maximum comfort, mean comfort, or minimum comfort. And obviously the red range is look out. That's high risk, okay? So if we looked at this acceleration, which is way below, we're right in here near 0. So we're at maximum comfort level. Again, if we look in the lateral or transverse direction of the bridge, again, we're very low acceleration, and we are in this here area. So we are avoiding vibrational troubles only with a little bit of low risk of troubles, and we're at maximum comfort according to this document. Now we're going to show you an assembly. That was some of the facets of design. We'll continue to talk about another facet of design with the assembly and testing. So I just want to show you a video here. We assembled this in our yard. You saw some pictures already. We're going to show here, give you a minute. We're going to assemble it from the bottom to the top. You'll see things under each bay. We pre-camber our structures upward, just like a pre-stressed concrete bridge is pre-cambered upward with their stress in their pre-stressing strands. We pre-camber our bridges, and we have a technique to do that, a geometrical technique, placing the holes of our cross bracing. Another critical factor, we wanted to match the lift that was going to happen in Bermuda, and we wanted to make sure there was no problems. Here is our lift, approximately 20 feet in the air, which was the required lift. Our crane is from a local crane company that lifts manufactured homes. Well, this was probably the longest manufactured home they ever lifted. So this was critical logistics. Bermuda was limited by the cranes, as I said before, and as part of the test program, we lifted this bridge and simulated the Bermuda pick in our yard. There are 8 pick points, and maybe I can show you them quickly. As you can see, there's a line, there's a pick point. If you see blue on the structure, there's a pick point, pick point, pick. This was just a stability point that we added. So really we have 1, 2, 3, 4. So we have 8 pick points, 4 on each side. Essentially, Tucker was with us during this. He came and visited us, helped us assemble the bridge with us, and he watched this pick. So all this from the pick point down, we sent all this equipment so that Tucker could match that lift in Bermuda. Moving on, in order to simulate the uniform live load of 72, remember we increased it 110%, the 72 pounds per square foot, we created pools and we filled them to safely apply the uniform live load. So as you can see, we have pools here, we're filling them with water and the load is being applied. Here is a picture of that bridge. It's fully loaded. As you can see, it deflected. And just to make a note, here is at the abutment, at the bearing, no anchorage is secured yet. So it's a free rotating structure. The final condition in Bermuda, there will be anchors here on the bottom cord and anchors here on the outriggers. There are 3 outriggers on each side of our box. And so that will not shown in this picture, but so there is extensive anchorage. We took the deflection. Deflection is a big deal for FRP members because often it controls the design. Not so much in this structure because it's a box structure. Section really helped us. But if you have a U-type structure, deflection will control. And we want our model to correlate with the deflections that we had. So we measured deflections. We found about 5 inches. The model showed around 7 inches total with dead and live load. So, but we believe that to be okay because our model does not consider the rigidity of the decking. So this 5 inches, which was a little lower than 7 inches, we were quite pleased with that when we did the testing of the dead plus live. Moving on to installation. The bridge was disassembled. It was kitted or packaged up and shipped to Bermuda in containers. We reassembled, Tucker, which is going to continue, he reassembled the job. We couldn't go to Bermuda because of the pandemic. We were not allowed to be on the island. It was closed. And so we shipped the bridge to Bermuda for Tucker to install, assemble and install. Bart, he then assembled it, which you will see. He barged it to the piers and then lifted it into place. Tucker?
Thank you, Dan. That was a very informative piece on the design and some of the technical issues of the bridge. I'm just going to talk a little bit about putting the bridge together on site and how we got it to our final location. And as Dan mentioned, I had the good fortune to build this bridge twice and disassemble it once. So I traveled to Pennsylvania during the height of the pandemic in August of 2020, and then I came back and the bridges arrived in October 2020. They were shipped in 3 containers, and our staging location was at the western end of Bermuda, a place called Dockyard, which was actually, it was home to America's Cup in 2017. And it was really an ideal area for us in many ways because it was, you know, it's pretty wide open, an easy area to work. One of the challenges was we had to be near enough to the water to have the barge pull up and be able to pick the bridge, which left us quite exposed to the conditions. So any storm that came through, we really felt. But the bridge, once it arrived in Bermuda, it was constructed entirely by a team of volunteers. Volunteers, and we had one a telehandler or a forklift could also work. The volunteers were an eclectic group of people. It was a mix of young and old, women and men. I think our oldest volunteer was 80 years old. And we even had a fellow who was, he had been stranded in Bermuda on his boat during the pandemic in Dockyard, and he had nothing to do, so he just came out and helped us put the bridge together. So almost anyone can do it. And as Dan mentioned, it's very lightweight, so it only took 2 or 3 people to carry each piece of the bridge. Once we assembled it, we picked it up, put it on this barge. As you can see, the barge, that was probably the most stressful part. I think we were pressed by time to get everything done in time to get it on the barge. And we were fortunate that we had done the lift. We had done the lift before in Pennsylvania. We knew exactly what the equipment was. The only factor we couldn't control is we hadn't put it on a barge before, and that was the most stressful thing, I think, watching the bridge leave the dock on the barge. You just hope that it would not be lost at sea and not become a bridge for fishes instead of people. But we had a calm day, so everything arrived okay on site. And the installation went very smoothly. Our anchor bolts aligned perfectly, and the installation itself actually only took a morning. And here you can see the bridge in place. It's got about a 20-foot clearance once it's in place for boats underneath. So here's just a short video of the installation. Dan's going to start it. It's speeded up slightly, but it really is quick. So we just lined the bridge, the barge up, anchored it. On the pylons, we had the contractor who built the pylons, and then the barge was obviously contracted out as well.
Yeah, Tucker, that was installed, as the video says, on December 14th, 2020.
Yep. And it was a big event in Bermuda, the local news station. This is where the video is coming from. They were there to capture it. So everything, we were fortunate that everything went smoothly. And actually, we also had a video that created Pultrusions. They could not be there at the time because of the pandemic, or restrictions were quite severe at the time. So they were watching remotely and guiding us on any questions we had.
Hey, Tucker, do you know what that boat did?
He was just guiding the barge. So here the bridge is what it looks like in place at Flats Inlet. We felt like it fit with our original railway motif pretty well. There's still a couple elements that have to be added after this picture. There's some diagonal pieces coming down, which Dan is illustrating. And people seem to like the aesthetic. It appears more lightweight than we originally imagined when we drew it up, and fairly transparent. And there are also wonderful views. It's kind of opened up, as I said before, more of the turquoise sea of Bermuda to locals and tourists alike. Here he's looking off the main span. This inlet is notorious for eagle rays, which go underneath. So you have a wonderful overhead perspective onto them.
I just wanted to go over a little bit of the lessons learned. Again, we assembled it in our yard and it wasn't level. We used these concrete barriers that have pointed edges on them, as you can see. And when we started doing the test, one of the corners, the knife of that barrier started coming into our material. And because of the higher stresses there at that point, it started propagating a crack in our bottom cord. So we went back and decided to firm that up, as you can see here, and we firmed that area up. The numbers or design numbers were okay in this area. It's just that localized hinge point, or a jackknifing point, you might say, caused some troubles. And so we decided to reinforce that a little better and take care of that problem. And the testing that you saw earlier had that in effect, the photos before. So we took care of all that. Now it's time to hit the trail. Anyone want to come with us? Any questions or inquiries? As you can see, our emails are there and in the slides. Again, I will take technical questions, and Tucker will take questions regarding for the owner or anything like that. Or, as I said, he was there constructing this bridge in Bermuda.
All right, Dan and Tucker, thanks a lot. Very interesting presentation. In fact, very interesting concept for a very lightweight bridge. So at this point, we're gonna turn it to Paul Lyles, who's gonna be moderating the question and answer. Paul?
Okay, thank you, Torrid. And Tucker and Dan, real good job. Okay, we had some questions that came in beforehand, and we've got some more that have come in during the presentation. We'll probably get some more during the question and answers. But I've broken the questions down into design questions, construction questions, maybe a couple maintenance questions, and some cost questions. And with that, we'll go ahead and get underway. The first one, design questions. Could you discuss climate change and resiliency in respect to the project?
Sure, I can field that one, Dan. Well, in terms of climate change, I mean, it depends how far you're looking in the future. I I think Bermuda itself we're really in a lot of trouble when it comes to climate change. We're a low-lying island. The bridge itself is quite high, and it's high for other reasons as well, primarily for boat access. So I think we have sufficient. I mean, in terms of the main span itself, we have sufficient height that it wasn't as big an issue. Other things in Bermuda, unfortunately, will disappear long before this bridge. At Bailey's Bay, it was a lower bridge that was more of a consideration. There, basically, we went as high as we could while trying to mitigate, issues such as the views of the neighbors who live in close proximity to the bridge. Our biggest concern there would be waves during a big hurricane. But because it's on the north side of the island, it's less likely to be hit as on the southwest side.
Yeah, if I could just interject one comment. I think FRP material, since it is ductile, enhances its ability to resist hurricane forces and such. So.
Okay. The question came in beforehand on the bolts, and you mentioned the stainless steel bolts, but the question was, did you use any fiberglass bolts at all on the bridge?
Simply put, I think the strength of those were not what we needed for this bridge, and that minimized bolts in our connections if we used the steel. So we chose to go the route of the high strength stainless steel bolts rather than the fiberglass. Okay.
There was a question that came in beforehand about, can you discuss the FRP truss connections? You mentioned those in the presentation and the testing. Do you want to add anything to that at all?
No, that's pretty much how we make sure we test what we put out there. So.
Okay. There was a question involving that came in during the talk, and does the connection design include some safety factor when you have the test results?
Yes, there is a difference. If we would design your bridge for the ASTA guides specifications FRP, your safety factor would be 4 as prescribed. With the International Building Code, we utilize 3, generally speaking, 3 for connections. So these connections on this bridge have a safety factor of 3.
Okay. One that came in beforehand, it says, can you discuss the analysis, code checks, calculation of stress ratios, design drawings, contract notes, and special provisions for this project?
Actually, I sealed the plans for Pennsylvania and with my state seal. And well, actually, then we had a third party. So the design checks, the analysis, as I said before, was run by Rick, the former owner of Techtonics. He ran his instead. I ran my analysis in RESA. The RESA analysis was the official analysis. So we did all this. I mean, we must have ran the thing 30 or 40 times in different ways. We checked offsets of all the members coming into other members. Code checks was all based on International Building Code. We checked all the members for tension and compression. Again, Euler buckling, okay? So all those calculations were part of the design package that was then sealed to Bermuda, and then a Bermuda engineer was okay with them, and then he submitted them to the government, the owner of the bridge.
Okay.
Just to chime in very briefly, it was very important to us as a client to have the independent consultant sign off on everything, and also to have the full-scale load test. That was the most crucial thing for us, and the independent consultant was there for the full scale load test.
Okay. Question that came in beforehand was what design code was used? You mentioned that you used the International Bridge Building Code, and then also the question was it designed for high winds? And you mentioned the hurricane winds, but what about earthquakes?
Earthquake was looked at, but the wind controlled over the earthquake loads.
Okay.
So.
Okay, and the next question was beforehand, what material specifications and properties were used for the FRP shapes?
Those shapes can be seen in our Pultex manual. I don't know if the questionee knows it, but in our industry, you would design based on the properties of your manufacturer at this time, because there isn't a standard set of properties that you would design by. So they design by creative Pultrusions manufactured products.
Okay. How can we apply this technology in our soon to be real world projects?
Well, if you have any project near that is in a salty environment, corrosive, this is the ideal material to use. Many parks and recs use our material because it's lightweight, easy to assemble, and easy to put in place. So that's how we use it in real world, and that's why this was started. Rick saw this in the future, and it is. We have over 1,000 bridges in place and increasing every year. So.
Oh, okay. Can Pultruded bridges be used to rehab or replace movable bridges?
Oftentimes decking. Pultruded decking can be used, but also another process, our sister company does vacuum infused fiberglass decking. And they will use that decking on a steel structure. Because it's lightweight, the design's going to be less, the weight's less. And so that is where it really comes into play, FRP material. And yes, we do have some projects where we've been incorporated into lift bridges, twist bridges, all that, movable bridges, types of movable bridges. Our lightweight material can be incorporated into the design.
Okay.
And has been.
All right. Question that came in beforehand, what are the limits on length and width and weight for these bridges? And can you also use them for vehicular bridges?
As you can see in our one slide, we generally go up to 12, 14 feet. We are pushing those limits, but we're investigating those limitations as we speak, but that's your width limit. The length limit is right now 150 feet. Maybe we want to go farther. You have a job out there, we'll look at it. Generally speaking, these bridges are not used for vehicular bridges. Our limits now are about H10, H15 trucks, and that's what you see for pedestrian bridges.
Okay. Here's a question that came in during the talk. Does Bermuda have local wind speed data for design purposes?
We measure local wind speed during hurricanes, but we just go by the requirements that Dan outlined. So the 158.
Okay. Another question that came in during the talk, could you talk about the need for the FRP bridge as opposed to maybe a pre-stressed concrete bridge?
Sure. I mean, from our perspective, we were looking at kind of the lightest weight and the easiest to construct. I think we had to consider as well just our capabilities in construction. For example, for the pylons themselves, we hired a local contractor for something that is bigger or more complex. Oftentimes you have to outsource it. For example, our airport was outsourced to a largely Canadian firm. And we're a relatively small charity, so we were also looking at being cost efficient.
Okay. The question came in about during the talk. Do you know the thermal coefficient for the FRP material, maybe compared to steel or concrete?
Yeah, I can tell you this, it's less. So I'm not going to quote it, but in our Pultrudes manual, it's there. And it is less than steel and concrete, similar to concrete.
Okay. All right, let's look at some questions that came in on our construction beforehand. The first one, did the use of the FRP Pultruded composites save time in assembly and installation and make the client happy?
That's for you, Tucker. You're the client.
I would say it's hard to say. I mean, in terms of shipping, I mean, it would obviously be easier to ship a completely prefabricated. You know, you ship a prefabricated thing down and you install it. The hard part is the expense and also just getting something that big. For example, this bridge we talked about leaving it assembled and trying to ship it to Bermuda. We weren't able to do that because it wouldn't, you know, fit on the road and also on the ship itself. So from that perspective, it was much easier. And in terms of the assembly itself, I would say it took us. I mean, we worked during mornings with volunteers. It didn't take us very long, and I think the advantage is that a lot of our volunteers took ownership of the bridge itself because they were spending their time and effort assembling the bridge. There was a lot of buy-in, particularly during the pandemic. I think people were eager to get outside and do something productive. Okay.
You had a question here about what was the total weight of the bridge. I think you mentioned 60,000 pounds in your slides. And there was a question about the UV protection. And you mentioned you had an additive for it, and also you painted the top cords. You want to add anything to that at all? Was that pretty well covered?
That covers it.
Okay. Were there any claims or changes of plans during construction?
Changes of plans during construction of the bridge or construction of the
during construction.
Dan mentioned the one factor where we had that condition on the edge of the supports. Because of that, they reinforced the channel, the C10 channel. And that was all covered, I mean, in our original contract.
Okay. So a couple maintenance questions. Could you discuss the in situ repairability if it's hit by, say, a sailboat mast or something, or an errant maintenance vehicle?
Sure. So we've actually experienced that with one of the Bailey's Bay bridges during a hurricane. I believe it was either Faye or Gonzalo. It was 4 or 5 years ago. A fishing boat broke loose from its mooring in Bailey's Bay and ran broadside. It was pushed against the bridge during the hurricane for the whole storm. Sadly, the fishing boat broke apart. The bridge remained. It broke apart, sank, lost its engine, was a write-off. The bridge had some damage, primarily in the outriggers, some of the cross pieces, And the bottom cords, we contacted Creative Pultrusions and were able to replace all of the pieces that were damaged in place. And I think the insurance, it was covered under insurance, and I think it was around $10,000 total.
Okay. You replaced the outriggers. Is that what you did?
The outriggers, some of the bottom cords, and also the cross pieces, which come out and attach to the outriggers.
Okay. There was a question here that came in beforehand, and I see it also mentioned. What is the construction cost of the bridge? Do you have a cost on it at all?
I'm not going to reveal that, but I can tell you the value of this bridge is around $400,000 in the market today.
Okay. All right.
And so that's just the truss part. So.
Okay. That's fine. We got a lot of questions that have come in during the question and answering. So I'm going to ask Jugash if he could come in and pick up what we have here. Jugash?
Thank you, Paul. First question I'm going to ask is, you mentioned that natural frequencies, modes, and values in hertz were calculated. How were accelerations calculated, since the CETRA document table classifies the degree of comfort according to accelerations caused by the pedestrians?
Yeah, you do take that, their equations, whether the cosine or the sine, and you incorporate that in. So whoever asked that question could maybe get further clarification. But yeah, you can do that. That's in that document, how you calculate that.
Okay.
So.
What is the thermal coefficient of expansion for FRP compared to steel or concrete?
It's less.
Yes.
Or very similar to concrete, definitely less than steel. And it's in our manual. So if you go to the Pultex manual under the references, and you can see it in there for our members, channels and whatnot.
Okay, thank you. Next question, was uplift a concern in the design of the connections for the bridge?
Yes, we sent all that data to the engineer in Bermuda. So we coordinated all that and gave them reactions.
Okay, thank you. Next question, what collision protection have you provided?
Not really any that, besides what was structural to the project.
Yeah, in terms of the inlet itself, I mean, there's not really any. There are not really any boats. It's not an inlet. It's not like the Intercoastal Waterway or something which goes somewhere. It's mainly small center console watercrafts that go under the bridge, and the biggest boats are they belong to the local aquarium, and they're very aware of it.
Okay, thank you. Next question, have you considered earthquake load for the design?
Yeah, I think that.
Yeah, we don't really have any earthquakes, or they're not a big. Our biggest concern here is hurricanes.
Yeah,
Although
the hurricane wind controlled.
Okay, thank you. Next question, what is the design life for Pultruded FRP members?
75 years.
Okay, same as a typical bridge nowadays.
Yeah, 75.
Did you use?
80. Yeah.
Okay, thank you. Did you use A325 fasteners? And if they were used, were they galvanized? And what was the method of tightening?
No, we didn't use A325. We used A316. And so that is a good question about the tightening. We did not tighten to steel specifications. We hand tighten. And so the torque is a lot less required.
Okay, thank you. Next one. FRP is sensitive to any impact. Have you had any issues in transportation?
I'm trying to think. Not really. I think we had one X-brace it had a slight crack in it. and that was, we mentioned it to them, and they replaced it under warranty or under insurance.
I think that was during shipping, wasn't it?
Yeah, during shipping.
Okay.
Okay, thank you. Next, how did you reproduce the camber when reassembling the bridge?
So we, with all the bridges, we get assembly drawings from Creative Pultrusions. And on those assembly drawings, you also have the camber. So we used just wooden shims. They actually included the shims we used in Pennsylvania. And that was probably the most important part of building the bridge, is kind of how you lay it out. You ideally want as flat an area as possible. And to really, you have to get the camber. If you don't get the camber correct, then it will be very tough to put together.
Okay, next one. Thank you. It looks like wooden planks were used for the deck. Why FRP planks or panels were not used for the same durability as the truss?
Probably economy, correct, Tucker?
Economy and also aesthetic. There are a number of considerations. Aesthetics. We were concerned too with just whether FRP might be a bit slipperier, particularly in areas, if they became a little mossy or if there are algae attached to it. And people, we had built Bailey's Bay previously. People like the aesthetic of the wooden planks.
The next question I think you have already answered, but it refers to UV degrading of FRP. Is that design life impacted by that particular issue?
Can you repeat that question? I'm sorry, Judas.
The question is, what is the design life of FRP, which you've already answered, 75-year design life, but it says, with respect to UV degrading the FRP, in other words, is UV having an impact on the design life?
Yes. But it's still 75 years. We anticipate. You gotta remember, our bridges that are out there are only 20 some years old. So we can't tell you we've had our product out there for 75 years.
Okay.
So
Next question. Well, I am out of time, so we will address or answer the rest of the questions online on our website. So with that, I will turn it back to Adarad. Thank you for answering my questions. They were not mine, but from the audience.
Thank you, Julius.
All right. Thank you. Thank you for a great presentation. Thank you, Paul and Jogesh, for moderating the question and answer period. Again, thanks to our speaker. Very interesting presentation. Lots of interest. So again, for the 2022 ABC conference, it's going to be fully in person, no hybrid, no virtual. So hopefully we are done with that, and by December of the 2022, we will have the chance to see all of you with us in Miami, Florida. So on that note, we would like to conclude our February 2022 webinars, and hope to have you again with us for our next monthly webinar. Thank you.